All right. Hello. Happy Wednesday. I'm waiting for a delivery. We're getting a new bed. Fun. And of course, the delivery time is like right over class time of all the times. I'm free all day up until now, and then the window that they gave me. Anyways, so I might have to run open the door, but should be okay. The door's right there, so not a big deal. All right, so just as a quick kind of review, we talked about exponential equations, but also logarithms. And so what we said was that, and only because we'll refer to this later, so I want to have it here. So for positive b and a, and b not equal to 1, if we have something that says x equals log base b of a, sorry, that's a lowercase b, of a, that's the same as saying b to the x equals a. So x is called the logarithm, which is more obvious here, right? But even in this case, we would call it the exponent or the logarithm. And so you'll want to kind of keep track of, okay, well, the base here, the base on the log is going to be the same as the base on the exponent, right? And then the argument inside the log is equal to the exponential function. So let's see, we ended off, right. Oops. As a quick example, probably the hardest one that we didn't get to, but we'll start here and just kind of work into logarithms. We'll see similar problems anyway, so it doesn't matter. If I want you to solve something like 10 to the power of 5x plus 3 divided by 5, and if I tell you it equals 39, right? Whenever I say solve, really you're just solving for whatever variable is there, right? So if it says solve, you have to solve for x, right? So that's understood. So what you want to do is you want to shake out as much as you can until you're able to use these rules, right? So probably rewrite this as a log, right, is what it looks like, because I've got this x in the power, right? And so if I want to bring that x down, I have to rewrite it as a log. So what we can do, right, we can multiply both sides by 5, and so we get 10 to the power of 5x plus 3 is going to be, and I've already got it here, 39 times 5 is 195. Okay. So now, to kind of drop this x, so the 5x plus 3, if we write it in terms of this, right, our b is 10, so we're working in base 10. Our x is going to be replaced with 5x plus 3, and our a is going to be replaced with 195. So what we have is 5x plus 3 equals log base 10 of 195. So 5x plus 3 is log base 10 of 195. So definitely worth having on your cheat sheet are these, right? Because that's how we're going to move between the exponents and the logs. So now that I've brought this x downstairs, then there's, now we're back to kind of basics, right? even though we've got this log base 10 of 195, but that's just a number, right? This is the exact form of that number. You can use your calculator, calculator app, whatever. And now we can solve for x. So we've got 5x is the log base 10 of 195 minus 3. Recognizing that the log base 10 of 195, that's one thing, and then I'm subtracting 3. So you don't want to incorporate that minus 3 into the log. And then so x must be log base 10 of 195 minus 3 divided by 5. You don't need to have the log base 10, right? We talked about this is the common log, so a log base 10, you can just write log base e, you can write ln, and then for all the other bases, you would have to specify. You don't need it in brackets. It should be, so if what you were doing was log base 10 of 195 minus 3, so like this, you would need brackets, right? But because that's not what we're doing, it's safe to not have brackets. There's no harm in putting brackets around here, right? But you don't have to. It's me being lazy. So, good. Without logs, solving this for x would be very difficult, right? You'd have to figure out what x makes this happen, and I don't know if I'd be able to come up with anything like this. So logs are pretty useful. So for the next one, if we have to solve for x, if 1 equals 2e to the power of negative 0.1230, 425x. So again, we've got this x up in the power or in the exponent, and so we have to use logs to bring it down. Okay. Later on, what we'll do is we'll start taking the log of both sides, the appropriate log of both sides to bring down that power. I think that's the easiest way. The textbook, for some reason, doesn't want to introduce that, and I'm not sure why not, but they don't want to. So, but I will anyways, because I'm old school, I guess. I don't know. So, if I want to solve for x here, then what I need to do is I need to get everything that's not in this exponential equation over to the other side, right? So I need to divide both sides by 2 in order to get this thing on its own. So I get 1 over 2 is e to the negative 0.00425x. So now this is saying that, right, remember that phrase that we used for the exponent and the logs? So whatever's in the power, that's the log of the base that you're on. Anyways, of the argument. What was that nifty wording they used? X is the log or the exponent on a base e that gives the value a. Hey, that's not very groundbreaking. I don't know, I just find that more helpful. Truth be told though, I did do a math degree and then a master's degree in stats where we use a lot of exponents and logs, and I never had to remember this here. once we establish the log laws, you won't really need to remember this, right? Because I find it very confusing to move back and forth between these two. Now, I mean, years later of practice, I get it. But it doesn't come naturally to me. So I understand if it doesn't flow nicely, but we will have other ways to deal with it. So coping mechanisms, I guess. So let's see here. What do we got? Where are we at? Oh yeah, so this is the power. So what we have is we're going to take the log base e. That's the only time that I'm going to write the log base e, just to emphasize that I'm bringing this base down onto the log. Log base e of 1/2 is negative 0.000425 x. Log base e, right, is ln of 1/2, which is just a number. Negative 0.000425 x. Usually what I do a little switcheroo at some point because I always like to have the x on the left-hand side. But remember, the equal sign is just a revolving door, right? So if I want to have the x on the left-hand side, I can just switcheroo things. Usually I'll make a move in my switcheroo as well, so that can get confusing in the beginning. Something like this. X is the natural log of 1/2 divided by negative 0.00425. So what I did is I moved this over, so I divided both sides by this negative 0.00425, but then I also switched so that the x would be on the left-hand side and the stuff would be on the right-hand side. So if you use your calculator, then the natural log of 1/2 divided by negative 0.000425, I get approximately, so this here is the exact answer, right? Even though it doesn't look very nice. But x is approximately equal to 1,630.934542. Okay. So, good. So that's kind of the end of the review, let's call it, even though we didn't do anything quite this large last day. Oh yeah, so if you have to put this into a calculator, I'll show you on the Desmos app calculator, blah, blah, blah thing here. Clear all there. So if I have to take the natural log, there's an ln button here, ln of 1 divided by 2. Make sure it stays inside the log there. End bracket, and then divide that by negative 0.00425. And then it gives the approximation. I don't have a pointer on here, but you should see the 1630.934542. Good. So as long as you make sure that your log, yeah, Desmos, it's doing pretty well so far. Except they really want you to use the change of base formula instead of the just giving you any base on the log. But anyways, we know how to deal with that. So. All right. Let's see here. 10.2, our last section in chapter 10, even though I think chapter 10 is probably the, I would almost say the easiest chapter. We're in and we're out. Wham, bam. Thank you, ma'am. logarithmic equations. Oops. So we talked about, yeah, chapter 10. It was so accessible. I'm not going to say easy because there's a lot of laws and rules that we have to remember, but as long as you keep plugging away, yeah, gone but not forgotten. Well, we'll throw on a test too, so it'll be here. So logarithmic, no? Oh, okay, well, well, if I don't have to, I'll go by feel. What grade should this person get? So logarithmic equations, we already talked about logs earlier, right? But logarithmic equations are when we have logs and we have to solve for things inside the logs or involving logs. So I'm about to tell you the moneymakers for solving these logarithmic equations. And so, of course, they're called the fundamental properties of logarithms. Sounds important. It is, or they are. There's only two, or there are only two, I should say. The first one is that the log base b of b to the power of x is just x. You're right, Riley. Oh, sorry, Reed. It was Reed. Fundamentals. So what's this saying here? Log base b of b to the power of x is just going to simplify to x. How would we use that? Well, if I have something like 2 to the power of x equals 4, oh, that's stupid. Well, I guess it's fine. It doesn't matter. Let's say 15. Right, 2 to the power of x is 15. What can I do here? I could take the log of both sides, right? I could take the log base 2 of both sides, because as long as I have the same base here and the same base here, then the log base 2 of 2 to the power of x by this property is just going to be x, right? So everything else drops down. So then I can take the log base 2, I'll say take log base b of both sides. Right, as long as you do it to both sides, you're safe. Log base 2 of 2 to the x, log base b of b to the x equals x. Log base 2 of 2 to the x equals x. Right, so these essentially cancel each other out. So this drops down here. X is log base 2 of 15. Okay. Which, from our change of base formula, right, you could evaluate using either log base 10 or log base e, because those are the buttons that we have, right? And so I should stick with the same color. X is going to be log of 15 over the log of 2. hope I didn't switch those up. I didn't. I'm not sure what you mean, Dermot. Are we required to know the depravities of the rules? Depravities. Using a word I don't know. Oh, like the proofs for them? No, you don't have to do any proofs. We'll do a couple of proofs, or I've got one up my sleeve for today. These proofs are actually pretty easy, but no. I do expect you to be able to use it like this though, right? Yeah. Because this is just, I'm just showing you how you would use this fundamental property in solving for x. Right? So instead of doing it like we did, I think, yeah, like we did last day, we solved something like this, but I just find it's easier to just take the log of both sides, the log of the appropriate base. And then because we don't have a log base 2 button, we have to convert this to log base, so log base 10 or log base e of 15, and then same log of 2. So we get log of 15 divided by the log of 2. Roughly 3.906890596. I'm going to cheat and do it on here. Log base 2 of 15. X is approximately equal to 3.9068900596 using my calculator. Okay, so we use this property to be able to bring down an x if we're solving for x. Use this property to solve for x in the exponent. Symbolab.com. Checking it out. Hey, cool, nice. That's great. Yeah, so it seems to have log base whatever you want, which is really nice. Same with this calculator. It has like a log with an empty space for the base, and then you can do whatever you want. So your calculator might have it if you have a calculator. Okay, so the second fundamental property is this. B to the power of log base b of x is equal to x. Okay. So how would we use this? Well, if I've got something, a log wrapped around an x, and I want to free that x, then what I do is I raise everything to the power of the same base as my log, and that's going to shake out my x. I want to use kind of the same terminology here. Use this property to solve for x in a log. Okay. So for a quick example, how do we use this? If I have something like the log base 4 of x equals 14, To shake out this x, right, what this property says is that, okay, well, I have to have the same base here, but if I raise both sides to the power 4 with a base of 4, so not to the power of 4, but it's typically how I say it, even though it's incorrect, right? So if I raise both sides on 4, I guess, like this, 4 to the power of log base 4 of x is 4 to the power of 14. As long as you're doing the same thing to both sides, they're still equivalent, right? So we're still allowed to do that. For some reason, my log looks a little wishy-washy here, so log base 4 of x. Okay. So what this is saying, again, we've got this kind of cancellation property, right? So we've got 4 to the power of log base 4 of x. B to the power of log base b of x is just x. So this essentially cancels these guys out, and the x is going to drop down on its own. So this means that x is 4 to the power of 14, which you can just do on your calculator. 4 to the power of 14 is huge, but it is exact at 2, 6, 8, 4, 3, 5, 4, 5, 6. Okay. So being able to shake out an x in a power or an x in a log, that's going to be really useful, right? So, so we need to know how to do that. And the fundamental properties are how we do it. Okay, so these are important. How do I put a, I'll do pink highlighter all around. Started off with the big leagues here. Okay. As an example. Okay. There's also, oh yeah, so the log base 4, so the 4 to the power of this one here. So these guys cancel out because of this fundamental property. So we're just applying this property that says that if you have b to the power of log base b of x, then these are essentially, in my mind, they cancel and you're just left with x, right? And so just like multiplication undoes division and vice versa, right? Now, raising something to the power of the base is going to undo the log. Okay. So this is going to be a really useful property. We don't use it in the sense that you're going to see something like this. You're going to force it to happen, right? So here, I'm forcing it to happen by raising both sides onto 4, right? So 4 to the power of the left-hand side equals 4 to the power of the right-hand side. So I'm just forcing that to happen so that I can shake out just the x. So kind of tricky. We've got some examples coming our way. So, but first, I don't know if that was, yeah, so here, the key is that you have to have the same base for both of these, right? So if it was log base 4 here, I have to raise, use 4 as my base for my exponent on both sides. I'll do another example. How about 3 log base 5 of, let's get crazy here, 1 over x equals 9. I don't have the proof prepared, and I'm not really sure how big it is. B to the log base b. So I don't want to head down that rabbit hole and muck it up. Let me see if I can see it though, because maybe it's here. I'm pretty sure it would just stem back to here. So if x is the log base b of a, then b to the power of x, plug this back in, right? Use this for a. B to the power of log base b of a equals a. I think they're just linked like that. But like I said, it doesn't really feel like a proper proof, does it? I'll have a, yeah. It's really just a cancellation property in my mind. So I guess it kind of makes sense that it would be as simple as plugging this into here and then nothing really changes because this is a definition, so I'm allowed to use that. I'll have to look at it on my own. How about that? I'll get back to you guys on Monday. Oh yeah, but let's try something like this. Isn't log just a ratio designed to be the inverse of exponents? Yeah, pretty much. It's like, so if you've got something in the power, the way you bring it down is using logs. And then you can do the opposite to solve for something inside the logs. So if you had to solve for x here, right? Then we'd first want to isolate the log, right? And so we can divide both sides by 3. I made it nice and easy on myself. 9 divided by 3 is 3. So then what I have to do in order to shake out this 1 over x in this case, I'm going to have to raise both sides onto 5, right? Because that's my base. So 5 is my base. So the only way that I can cancel this log base 5 is to raise it all to the power of 5. So I get 5 to the power of log base 5 of 1 over x is 5 to the power of 3. By that fundamental property, which we're allowed to just apply, right? This 5 to the power of log base 5 is essentially canceling out. And so you're left with 1 over x. So 1 over x equals, what's 5 to the power of 3? 125. Keep it on the same page here. 1 is 125 times x, right? Solving for x still, so I have to move this guy over, and then I have to shake the 125 over. I always just go ahead and multiply the x over to the right-hand side, and then I solve for x. I know that people are quicker than that, but for me, to play it safe, I always just bring the x over here and then bring the 125 over here. So I get x is 1 divided by 125. 1 over 1 over 120, sorry, 1 over 1 over 125. Ugh. Just 125. But it's because I made it weird. And I made it up. They're not always beautiful when I just make them up. Sometimes. Okay. So we'll do more. But for now, I'm just going to introduce it's called the log of both sides theorem. Essentially, it just says that if you have the log of the same base of two arguments, then those arguments are the same, as long as they're equal. So the log of both sides theorem says that, and so here we introduce a little important piece. If a, b, and lowercase b, so if capital A, capital B, and lowercase b are positive real numbers, and I'll come back to that because it's going to be important and it's part of the domain, are positive real numbers with b not equal to 1, so I don't want to look at a base of 1, then the log base b of a, if it's equal to the log base b of b, is equivalent to a equals b. Not that crazy, right? If you've got the log base b on both sides, then, and they're equal to each other, and that's the only thing that you've got on either side, well then a must be the same as b. But we use this property as well, so it's good to know. But it's pretty basic. Here's the important part of this thing. So from here, I want to make a note. Okay. What this is really saying is that a and b and the base have to be positive real numbers. So positive real numbers don't include 0. And you can try it on your calculator. You can try to take the log of 0. So the natural log of 0, I get a math error. Let's see here. Let's see what Desmos says. If I try to take the log of 0, undefined, that's even nicer. My calculator just says math error, mean. Undefined is so nice. So we can't take the log of error 2, cryptic. Error domain, hey, that's specific actually, because 0 is not in the domain. Yeah, error 1, that's gotta be something even worse than illegal math. So, only displays when the battery's dead. You can try taking the log of a negative number, but it's not going to work, right? And so, yeah, illegal math, taking the log of a negative number or a 0. So, you can try taking the log of -4, for example, and it will also be undefined, right? So, yeah, it's the error 2.0. So that's going to factor into our domains, right? If we're talking about the domains, the error or the error. Oh, Riley got it. Love a good pun. Say that 3 times fast. The fair-haired error. Get stuck in here. The fair-haired error. Okay, so one note, right? Especially if you're talking about, you know, what are some plausible answers. If you're solving for an argument here, so if you're solving for something inside a log, you better make sure that it's positive, right? So it can't be 0, it can't be negative. And same goes for the base, right? So the base and the arguments inside here cannot be 0 or negative. So we can't take the log of a negative nor 0. Right? The base must also be positive. Okay. So that's any log, right? We can't take the log of a negative and we can't take the log of 0. So that's going to factor into the domain. So when solving for values, right, either an argument inside a log, or a base, you need to make sure that your solutions satisfy this criteria. You need to make sure your solutions, potentially more than one, are positive. Are you positive? So even though it kind of stemmed out of kind of a basic fact, this part is really, really important. Any argument that you plug in there, any base has to be positive, which does not include 0. Okay. So we can kind of break these things down into 4 general types of logs and types of logarithmic equations that we need to be able to solve for. And so we'll go through those types, and then I'll do an example of each of them, right, and how we would solve them. So generally, logarithmic equations fall into 4 categories. The first one is where the unknown is the log. Unknown is the log. Okay. So the one that we're going to do there, I'll just put it down here so you have some sort of reference. If I tell you that log base 2 of root 3 equals x, right? That's when the unknown is just equal to the log. Right? Just as a heads up, right? How we're going to solve this, well, this is just a number, right? So we'll just solve it and then we'll have x. So that one's not so bad. We'll solve them formally, but just want to give you the lowdown. Another option is if the unknown is the base. Unknown is the base. Something that might look like log base x of 6 equals 2. The third option is the log of an unknown equals a number. Kind of a simplified version of the next one where it's going to be equal to a log. So if you have something like the natural log of x equals 5, and the last one, kind of last major category, is that the log of an unknown equals a log. So the one we're going to do for that one is something like log base 5 of x equals log base 5, 72. So how are we gonna do these? All right, so the first one, how we solve the first one, it was log base 2 of root 3 equals x. Right here, notice that this is just a number. So there's not really any tricks here that we need to do, but we need to remember how to solve for log base 2 of root 3. And so you could definitely use the, where was that link? The Symbol Lab link that Jaden posted. Or we could kick it old school and say that, okay, well then x must be equal to the log, or the natural log if you prefer, of root 3 over the log of 2. I don't know why I keep choosing log base 10 when I often just prefer to use the natural log, but it doesn't matter. In fact, you can try it on your calculator. It'll give you the same answer if you do ln of the root of 3, step it out, divided by ln of, as long as you use the same one, same log, 0.7924812.504 versus, let's see if I can swap these out. Same answer. And so it doesn't matter if you use a common log or the natural log, you'll get the same answer. X is approximately equal to 0.7924812.504. But this here is the exact answer, right? This is the approximate answer. Good. The second one was where the unknown was in the base, right? So we need to be able to tease out from the base this unknown value. So if we have something like log base x of 6 equals 2, what we're going to do is use the definition of a log, right? So if we have log base x of 6 equals 2, if we go all the way back to the beginning, right? Log base x of, what was it, 6 equals 2, I can rewrite that here, right? X to the power of, so the base is my x now. That could be confusing, right? But you just need to keep track of what these variables are. In fact, maybe I'll steal this here. Copy. I'm gonna get smaller. Use that to write it in non-logarithmic form. This here is the definition of a log. Definition of a logarithm. Right, but instead of me saying that, I figured it would be easier to just bring it in. So if we have log base x of 6 equals 2, well then our x is 2 if we kind of correspond these two, right? Log of our b is equal to x and our a is equal to 6, right? So what we have is we have x to the power of 2 equals 6. So I'll just write it here. Log base x of 6 equals 2 means that x to the power of 2 equals 6. Once you take the square root, right, we get the positive and the negative square root of 6, right? But this is one of those situations where the base has to be positive, and so it has to just be the positive root 6. So the negative root 6 is not an answer, or at least a viable solution. So the base must be positive. Therefore, x is the positive root 6. Yeah, that's the exact answer. I would probably just leave it as that. Well, leaving the plus minus, you're kind of missing that last step of checking to make sure that both your answers are in the domain. So you should take it all the way to the positive, if that makes sense. Okay. So the third one was if we have the natural log of x equals 5, right here, I've got x in my log, and it's equal to some number, right? but the natural log is the log base e. So what can I do from what we established earlier, right, is, okay, well, the natural log is log base e. So to kind of cancel this natural log, I would raise everything to the power of e. So here, I'll say cancel the natural log using e to the power of ln of x equals x. So if we have the natural log of x equals 5, if I take e to the ln of x equals e to the power of 5, e to the power of 5 is just a number, right? And so now I'm able to drop down this x, so x must be e to the power of 5. So x is approximately, I guess I didn't do an approximate answer, but for the previous one, but I want the exact answers. As often as possible, I want those exact answers. But let's use the Desmos calculator to do e to the power of 5, because I don't think we've done one yet. Clear all? There is an e to the power of x button. E to the power of 5. Oh yeah, so yeah, you're canceling because they kind of undo each other. So e to the power of 5 is roughly 148.4131591. I'll have to put it on here. I'll never remember that. There. 148.4131591. Technically, what I'm using here in this problem is the fundamental property here. Copy. I just realized I forgot to add a quick note to that fundamental property. We've already talked about it, but if you scroll back to, or if you go back to your fundamental property, here on the second property, I want to add that x is greater than 0. Because I'm taking the log of x, then it has to be greater than 0, right? We already talked about that, but just to be proper, we should have it somewhere on here as part of the domain. Good. Okay. So the fourth problem that we're gonna do was, where was it? Log base 5 of x equals log base 5 of 72. Nice. In this case, right, since these have the same base, log base 5, then we have the, what was it called? The log of both sides theorem, kind of a stupid theorem. Well, it's not stupid, it's obvious. But because these have the same base, I'm able to just kind of cancel them. Or if you prefer, you could take 5 to the power of both sides, right? And then they would both shake out. Either way, you're going to end up with x equals 72. So here, since the base is the same for both sides, we can use the same, we can use this so then x would just be equal to 72, right? So, or you could raise everything to the power of 5, right? So log base 5 of 72 is just a number, and you can find it by taking the log of 72 over the log of 5, right? So it's a little bit of work, but not bad. So this is just a number, and then if you raise 5 to the power of both sides, then this would shake out. You could leave it, it doesn't matter. So, or you could take 5 to the power of log base 5 of x equals 5 to the power of log base 5 of 72. In my mind, even though I would never really, like if I was submitting work, I wouldn't cancel like this, but in my mind, that's what I do, right? They cancel because they're the same base. So either way, x is equal to 72. So let's do kind of a harder one. If I have to solve log base 5 of x equals log base 3 of 72. Similar to what we just did, right? But now we don't have the same base anymore, right? And so we need to figure out what to do here. And this is where I would probably just go ahead, and because I want to shake out the x and I'm trying to solve for x, I would probably figure out what this number is and then take 5 to the power of that number as my x. And so here I get 5 to the power of log base 5 of x equals 5 to the power of log base 3 of 72. You can imagine these two kind of dropping out, and so the x drops down and it's on its own. So x, the exact answer is 5 to the power of log base 3 of 72. Nasty, but true. You'll want to practice putting something like that into your calculator, right? Whatever calculator you're using. So let's try in Desmos here. So I have 5 to the power of, so I want to make sure that it's all in the power. And in my power, I have the log base 3 of 72, which I'm going to have to evaluate because I don't have a log base 3 button. So I'm going to need to do brackets, okay, of the log of 72, end bracket, divided by the log of 3, my base was 3, and then step it out. Oops. That looks good. roughly 525.9481435. So x is approximately 525.9481435. Okay. Log laws. Bob log loves log log. The laws of logarithms. These are what make logs so fun to deal with because I don't know, it just feels like you can really control them for some reason, or maybe that's just me, but so fun. Capital F, fun. The laws of logarithms say that, okay, we're going to have to establish that if A, B, and B, so all our arguments on our basis have to be positive, but I have to establish it every time. So if A, B, and lowercase b are positive numbers, P is any, so lowercase p is any real number, and the base, I'm not going to let it be 1. The first rule says that if you have a log base b of a times b, that's going to be the same as the log base b of a plus the log base b of b. So that's really nice, especially if you're trying to simplify a log, right? If you've got the log of the same base, hey, it didn't write my, maybe I never wrote it. Right, as long as you have the same base, you're able to smush things together if you're adding logs of the same base. Okay. Similarly, if you have the log base b of a over b, you can write that as a subtraction. So log base b of a minus the log base b of b. And another frequent flyer is that if you have log base b of a to the power of p, you can drop that p in front or bring it back up if you have to, p times the log base b of a. So if you've got a power inside your argument, that's the same as the power times the log of the argument. So that's really useful. Log. I wonder if I still have my pogs. Probably. I'm a hoarder. Not actually, but got a lot of stuff. Pogs. My slammer. I used to have a really nice slammer, but I think it's gone. So, plugs. How do we use these? When do we want them? Now. Does anyone buy the plugs at the Rutland flea market? Maybe there's a market. It'll come, it'll come. My dog's making weird noises. I think she's just dreaming. Anyways. Okay, so we're gonna use these rules to simplify stuff. For example, write each statement as a single logarithm. First one, the log of x plus 5 log y minus the log of z. Second one, log base 2 of 3x minus 2 log base 2 of x plus log base 2 of x plus 3. Do I have another one? No. None of these. And give you a little bit of time with these rules. P is any real number. I've got it kind of there. Managed to get it on the same screen. So P is any real number. So any number. So if we start on the first one, maybe what I'll do is I'll just scoot this one down. Scoot. Right in between. So here, right, first thing I'm gonna do is I'm gonna make sure that I have the same base, right? Looks like I've got a base 10, base 10, base 10. So that means that I'm able to combine these things, right? So first thing you're gonna check is, do I have the same bases? Do I have any of the same bases? And those are the ones that you're gonna be able to contract. So we've got log base 10 of x plus 5 log y minus the log of z. So I'm adding and I'm subtracting log base 10s. So first thing I can do is I can bring this 5 to the power of y, right? Just to kind of clean up what this thing looks like. So this is the same as the log of x plus the log of y to the power of 5 minus the log of z. Because now I've got a log and a log and a log, and it doesn't really matter what's inside, but if things are being added inside that same log, I am multiplying, and if I'm subtracting, then I'm dividing. And because I end up multiplying and dividing, the order that I kind of smush these together doesn't matter. Right, I'm going to do it in 2 phases. If you just did it in 1, that's totally fine. But what I'm going to do is I'm going to combine these 2 first and then bring in my log z, my negative log z. So I get the log of x times y to the power of 5 minus the log of z. Right. Still checking, okay, log base 10, I'm able to combine these, right? And so what I get is, because I'm subtracting the logs, I get the log of xy to the power of 5 divided by z. And that's it. So now I've simplified this thing. And we'll do the same thing with the next one. This one's a little bit nastier, right? But first thing again that I'm gonna do is I'm just gonna make sure that I have the same base. If not, I have to deal with that. But for now, of course, we're going to log base 2, base 2, base 2. Okay, great. So I should be able to smush these all together into one log. So I've got the log of 3x minus 2 log x. But I can bring this 2 onto the power of x, right? So I can bring this back upstairs, and then the plus x plus 3. So what I get is, I'll just do this in a couple of different, or in a couple of rows, although you probably could smush it all together in one row. Sounds risky though. Smush. Log base 2 of x to the power of 2 plus log base 2 of x plus 3. Okay. So, like I said, because you're going to end up multiplying and dividing, the order that you do these doesn't matter, right? So I'm just going to put the first two together and then deal with the third one. So log base 2 of 3x minus log base 2 of x squared is the same as 3x divided by x squared. So log base 2 of 3x divided by x squared. That's going to simplify a little bit, right? X over x squared is just 1 over x, so 3 over x. But I'll leave it for now. It's just nice to make a note. Plus log base 2 of x plus 3. Okay. So what happens here, maybe I'll show it. This one cancels with this. Now I'm adding log base 2 plus log base 2. So I'm multiplying these things inside. So what I get is I get log base 2 of 3 times x plus 3 divided by x. After we canceled x over x squared to just be 1 over x. And then you're done. Let's do kind of a trickier one. If we have to solve for stuff, solve log base 8 of 3 plus 1/2 log base 8 of 25 equals log base 8 of x. Oh, could it be simplified further? I don't see anything obvious. As soon as you've got it as one log, because I think, so write each statement as a single logarithm. I don't think I would go any further. I wouldn't bother. You could 3 plus 9 over x. Yeah, that's good. I get lazy. I stop here. You could simplify it further. But because the goal was to find a single logarithm, you did it. Above and beyond. Yeah. If you tried to simplify this more. Just tap out. Here's good. Okay, so if we have to solve for x here, right, one thing that that I would do is, well, you have to make sure that you have the same base, right? Or at least just kind of scan it to make sure that you know if there's a different base in there that you have to deal with. So, all right, what can we do here? We can bring this 1/2 onto the 25, so 25 to the power of 1/2. That's the same as the square root of 25, right? And so we know that's 5. So we can simplify that a little bit. So let's go for this is equal to, well, I guess I can't use the equal sign. Why can't I use the equal sign? Because I've got an equal sign here. So it's weird to put an equal sign here, equals equals. So that's when I'm just going to write below. So log base 8 of 3 plus log base 8 of 25 to the 1/2 equals log base 8 of x. So the root of 25 is 5. So what we have is we have the log base 8 of 3 times 5 is equal to the log base 8 of x. Square root of 25 is 5, so I just did that in the same step as combining these when I'm adding these logs. So log base 8 of 3 times 5 is 15, so log base 8 of 15 is the same as log base 8 of x, but because these are the same base, right, I know that 15 must be equal to x, or x must be equal to 15. When you solve for an x like this, you should make sure that x is positive. It is, so it's good, right? So just as a little check-in, make sure x is positive. It is. Oh, what did I do to get 3 times 5? I'll deal with that one first. This is, so 25 to the 1/2 is the square root of 25, which is 5. And then I'm combining the bases. So that was for Jaden. And then Dermot, since the bases are the same, so you can't ditch them in the beginning here, but as soon as you have one base, so a log base 8 equals a log base 8, and that's all you have, then they can disappear. So here I could have just said 15 equals x, but I just wanted to show that they were the same. So if we have to solve something like, and I'll do the same thing again here so you can work at your own pace a little bit. Log 15 plus 2 equals the log of x plus 250. And then the second one where we're going to do is the log of 5 plus the log of 2x squared is equal to the log of x plus the log of 15. Smush. Very technical term, smush. Smush the math, smush the logs. So here, right? One thing that's kind of tricky is this 2 is not a log, right? 3. So here, right, I think you're here, Dermot, at this one. 3 plus the root of 25. It's not until you combine these, right, 3 times. Okay, so here. Okay, so we've got log base 8. So you can combine these logs, right? But the first thing you'd have to do is bring this power back upstairs onto the 25, right? So that's where the root of 25 is coming from. But then by the log laws, if you're adding 2 logs of the same base, then you can combine them into 1 log by multiplying inside, right? And then once you have them, so 3 times 5 is equal to x. As soon as you have the log of the same base on either side and they're equal to each other, then you can drop the log, but not until you've got this one single log. Cool. So I'll do the same thing here. I'll scoot this down. Whee! See how much space I need. So if I'm trying to solve for x here, right, what I need to do is I need to probably move this log over to this side, combine my logs into one thing, and then undo that one log. So that might look like, so what I'm going to do is I'm going to move this log 15 over here because I've got log base 10 and log base 10. So if I subtract the log 15 over to the right-hand side, I can leave this 2 alone. 2 isn't a log, so it could give us some trouble, right? But I'm just going to use it and keep it on the one side and move my logs to the other side. So here, what I get is 2 is equal to the log of x plus 250 minus the log of 15. By those log laws, log base 10 minus log base 10, I can write them as a single log by dividing the arguments. So 2 is equal to the log of x plus 250 divided by 15. Okay. I guess I'll need a little bit more room than this. Whee! Now I'm back to that scenario where I need to kind of shake this log out, right? I've got just the log and I want to get rid of it. I want to cancel it in a way. And so log base 10 means that I'm going to take 10 to the power of the log as well as 10 to the power of 2. So you're going to take 10 to the power of both sides. So 10 to the power of 2 is equal to 10 to the power of the log of x plus 250 divided by 15. And that's all inside the log. I made it kind of messy there, but it's the same as above, right? This 10 to the power of log base 10, right? The base 10 is hidden, but it's there, right? These are essentially going to cancel. I don't really love doing that. Technically not correct. But it's a nice visual, right? So 10 to the power of 2 is 100 is equal to x plus 250 divided by 15. All of a sudden, this is a very reasonable math problem, right? We've got 100 times 15 if we're solving for x. And so we've got 1500 is x plus 250. Let's do 2 more lines. So x is going to be 1500 minus 250. X is 1250. You always just want to check. Okay, so x in this case, x is going into a log, right? And so here, the answer for x has to be give a log that's greater than 0. And so x must be greater than negative 250, which it definitely is in this case, right? And so we're safe. Right? But you just have that internal check, especially if you've got multiple answers, then definitely check. This one, even trickier, right? Because you've got x's kind of in multiple locations, but a nice part is that you've got a log base 10, log base 10, log base 10, log base 10. So you've got the same base everywhere. So you should be able to combine these into a single log, right? You might want to keep it as two separate logs, one with just numbers and one with x's, right? Because you're trying to solve for x. But knowing that they're the same base is really useful. So what I'm going to do is I'm going to move my x logs to the left-hand side and my number logs over to the right-hand side. So I get the log of 2x squared minus the log of x is equal to, and I should stack my, wait, undo. Should stack my equal signs a little bit better. So the log of 2x squared minus the log of x is equal to the log of 15 minus the log of 5. Oops. I'm subtracting logs of the same base, so that means I can combine them by dividing the arguments. Same thing over here. So I get the log of 2x squared divided by x is the log of 15 divided by 5. Checking this out, 2x squared divided by x, the squared and the x in the denominator cancel, and 15 divided by 5 is, of course, 3. So what you have is you have the log of 2x is the log of 3, but because these are the same base, 1, 2, 3, you could cancel the logs here. You could say that 2x squared over x is 15 over 5. I would probably prefer to keep it just a little bit longer, but you definitely could cancel these logs and kind of do away with them here. But I kept them for one more line. Because now we can say that 2x equals 3, which means that x is 3 divided by 2. And just making sure where x is going back in, right? X is going straight into a log, and 2x squared is going into a log. But this is probably the one I need to worry about the most. I need to make sure that it's greater than 0, which it is. The last thing I wanted to do was prove the change of base theorem, just because it's a quick little show and tell. But it also kind of brings back the change of base theorem, because we're going to need to use it, especially if you're just using a normal calculator with only logs and natural logs. So if we have to prove prove the change of base theorem, which says that the log base A of x we can rewrite as the log base B of x over the log base B of A. So this is the change of base theorem, and this is what we've been using when we had to find things like the log base 2 of root 3, things like that. Right? We just pick an easy value of B over here. As long as we're using the same one, we're okay. So then what I'm going to do here is I'm going to let y equal this side. So here's my proof in a different color. Let y be the log base A of x. If y is equal to the log base A of x, then from here, I can rewrite this as a to the power of y equals x. Then a to the power of y equals x. If I take the log base b at both sides, right, if I'm trying to solve for y again here, but in a kind of a sneaky way, then I would need to take the log of both sides. So take the log base b of both sides. So then we get the log base b of a to the power of y is the log base b of x. This is kind of the reverse of what we've been using recently, right? We've been saying, okay, that means these can go away, but I can put the log base b back on and it's equivalent. Now I can bring this y downstairs, right? That's the third log law, is that the power can be rewritten. So I have y times the log base b of a is the log base b of x, and then solve for y is the log base b of x over the log base b of a. Don't worry, that proof was just for fun, but also as an exercise in kind of working with logs and seeing how they all tie together. Very satisfying. So logs are really fun, and I wish we could spend more time in this chapter, but that's all I have today. I've robbed you of your time before though, so I don't feel bad ending early. It's only slightly early anyways. I can do better. Are there any questions? Logs, so fun. I know. Yeah, where is everyone? I feel like, I'm not sure. Must be a weird, or do you guys have a lot of midterms? Oh, everyone's just taking a break. Oh, then I don't know. But anyways, I gotta let you guys go because I'm pretty sure my delivery's calling. Hello. Great, how are you? Yes.